all the planets we know, ours is unique. The only one with water. We take it for granted, but without this magic liquid, life couldn't exist. Where our water comes from is one of science's greatest mysteries. From deep inside the Earth to the far reaches of space, the search begins for the source of our water. Earth is the only planet in the solar system with liquid water. 330 million cubic miles of it. It covers over 70% of the planet. It even makes up about 60% of our bodies. We know a lot about water, except where it comes from.
When we think about where Earth's water came from, it's not that simple, because we think that all the building blocks of Earth were probably completely dry.
If Earth forms without water, then where do our oceans come from?
It's a bit like a crime scene. The crime occurred a long time ago and the evidence has been tampered with. So it's very much like being a detective. You've got to look back in time to try and understand what was going on 4.5 billion years ago. It's a hard problem.
For the first time, scientists from different disciplines are working together to find the origin of Earth's water. The answer has the most amazing implications.
We know of no organism that does not require liquid water to live. And therefore, when we ask, how did a planet acquire its water? In essence, we're hinting at the question of what makes a planet able to support life.
In order to unravel this mystery, we must go back in time and look for clues at the birth of the solar system. 4.6 billion years ago, our sun is a newborn star, surrounded by a vast disk of gas and dust. Over millions of years, this disk of matter condenses to form the planets. Far from the sun, it's so cold, planets like Jupiter form with icy cores. Closer to the sun, it's more than 1,000 degrees hotter than it is today. Earth forms from substances that condense at high temperatures, like rock and iron. It's too hot for water. Earth is bone dry. For scientists, one possibility is that water was delivered by comets. From the frozen wastes of our outer solar system, they're mostly ice. Toby Owen has been studying comets for over 40 years.
As soon as people figured out that comets had a huge amount of ice in them, then it seemed reasonable that comets striking the Earth would have brought that ice with them, and so that ice could have melted and produced the oceans.
For 600 million years, the early Earth is bombarded by hundreds of millions of icy comets.
Comets are very primitive bodies. That's what makes them so especially interesting. The ice in comets is ice that has been untouched since the solar system formed.
So if comets brought all of Earth's water, then the water we drink, wash, and swim in fact, the water that makes up our bodies, is older than the planet itself and is from the edge of the solar system. But the evidence is still circumstantial.
We need some clues to discover how the Earth got water. We need some clues in the water on the Earth that we can relate to other things, like comets, to see if we can decide what brought the water in.
Luckily, water contains the perfect clues. To the naked eye, water looks the same, but there are subtle differences depending on where it comes from. All water molecules are made of 1 part oxygen and 2 parts hydrogen. But the hydrogen comes in 2 forms. The bulk of hydrogen in water is normal or light, but a tiny fraction, the blue bits, are heavy hydrogen. The ratio of heavy to light tells scientists where the water comes from.
You and I, and all the animals, and all the trees, and all the oceans, and all the lakes, and the rivers on the Earth have the same ratio of heavy hydrogen to light hydrogen. That's our water. That's the water of the Earth. So the question is, what is that ratio like in the kinds of objects that could bring the water to the Earth?
To find the ratio of heavy to light hydrogen in the water on a comet, scientists need to get a sample. Easier said than done.
One of the things that made people so interested in comets is that they're completely different from anything else in the sky. Suddenly, from nowhere, this huge bright object appears and moves through the sky and then disappears again.
Because astronomers never know when they'll show up, most comets are out of reach.
You'd have to keep a spacecraft in your garage, something like that, ready to go at any minute when one of those comets appears.
But one comet has a special place in astronomers' hearts. It's not the biggest or the brightest, but it is predictable.
Halley's Comet is special because it's a big comet, and still it is one whose orbit we know. So that means we can predict when it's coming back to the Earth. We can make that prediction very well.
In 1986, Halley was once again within reach, close enough to grab a sample. For Dr. Carey Liss, just seeing Halley's Comet was the chance of a lifetime.
I actually was excited about Halley's Comet, and at 1 in the morning we were out there looking out in the sky, and I remember to this day we saw Halley's Comet really nicely, and that was very inspirational to me.
Because scientists knew where Halley would be, they could build a space probe for a rendezvous. The probe Giotto was designed to fly through Halley's tail.
One of the most exciting things that Halley gave us was not just here's a comet, here's what a comet looks like, here's the structure, but we could start doing chemistry. We could start understanding the composition of the comet.
Finally, scientists can analyze comet water and discover if it's the same as the water on Earth. On March 13, 1986, after traveling for 8 months, Giotto enters the tail of Halley's Comet. Then a crisis. Giotto hits a large particle of dust, traveling at 42 miles per second. Communications with the probe are intermittent.
There was a tense moment there when people thought the whole thing might be lost.
32 minutes later, communications are restored. The probe samples the water vapor in Halley's tail and sends the data back to mission control. Astronomers are about to find out if the water on a comet is the same as the water on Earth. But when the results come back, the mystery only deepens.
And what we discovered, to our surprise, was that the hydrogen in the cometary water was about twice as massive as the hydrogen in water on the Earth.
With twice as much heavy hydrogen, the water on Halley's Comet is not the same as the water on Earth. While it looks, tastes, and behaves just like Earth's water, to scientists, this difference is crucial. It can only mean one thing. Comets can't have brought all of Earth's water.
Well, that's a big, exciting result. It kind of defeats this lovely idea that comets brought all the water to the Earth.
In terms of did comets bring water to the Earth, it was a revolution and a change. And that's pretty exciting.
For years, scientists thought that comets were the source of all the Earth's water. But the evidence now makes this impossible.
So that was a very exciting result because it meant that you had to have some other source of water to produce the oceans that we see. And now we were going to have to go through the excitement of trying to figure out what really happened.
In 2002, a chance discovery suggests the answer might be closer to home. When the Earth first forms 4.5 billion years ago, it's too hot to form with water. But the planet has water now. If it wasn't delivered by comets, then has it been here all along? To find out where the water comes from, Professor Stephen Moyges is looking for clues to when it first appears. As a geologist, he uncovers the planet's past by looking at its rocks. But the past has a big hole. It's called the Hadean, or Dark Period, because nobody knows anything about it.
The problem of the first 500 million years of Earth history for geologists has always been that you have a nightmare scenario where you don't have any rocks or minerals to investigate.
It's thought early Earth is a fireball of molten rock, but with no evidence from this time, it's just a theory. Then in 2002, Moyges makes an earth-shaking discovery: the oldest mineral sample ever found on our planet, a crystal of zircon. Locked inside these tiny grains is a vital clue. Chemical analysis of zircon crystals reveals whether they formed in the presence of water. Over 7 years, Moyges finds and dates nearly 100,000 crystals of zircon. One stands alone.
The oldest one that we've found so far is 4.38 billion years old. Now, I'd like that to sink in.
When this crystal was made, the Earth was just 180 million years old. If this line represents the age of the Earth, then the dinosaurs died out here. Rewind about 4 billion years to the end of the Dark Period. The zircon crystal was formed here.
We're talking about time spans that are beyond comprehension. So for instance, in this rock here, there are zircon crystals that are 1/3 of the age of the universe. So these things have been around for almost as long as the Earth has been a planet. Talk about time capsules.
Analysis shows this 4.4 billion year old zircon crystal forms in liquid water. Rather than a dry planet, the crystal reveals that early Earth already has water on its surface.
When we made the discovery, that was very, very exciting because it wasn't fulfilling a hunch, it was true discovery. We didn't know what we would find.
For years, scientists thought that planet Earth forms dry. Moyges' discovery means that theory is wrong. Professor Mike Drake is searching for a new theory about how the early Earth forms wet.
Now, zircons tell you for sure when liquid water had to be present, and that's at about 4.4 billion years ago. And all of a sudden, we don't know where it came from. We've suddenly got a major problem. We have to seriously consider the possibility that water was present in the building blocks of the planet as it formed.
But how could water exist in the building blocks if the blocks were boiling hot? The answer requires another step back in time.
I finally went back to what the system looked like 4.5 billion years ago before there were any planets, and realized we had these fine grains of dust embedded in a sea of hydrogen and helium and oxygen, and some of the hydrogen and oxygen reacted to make water. So we basically had dust surrounded by water.
Over millions of years, the dust and gas condenses to form the planets in the solar system. Far from the Sun, Jupiter and Saturn form with icy cores. But ice isn't the only way planets can lock in water. Further in, where it's too hot for ice, water can be locked into rocks, as this mineral demonstrates.
If you look at it, it looks really dry. If you touch it with your fingers, it's really dry.
But heat unlocks its secret.
And now you can start to see it's really boiling up into little balls of water. There's a huge amount of water coming off of this mineral. So a perfectly dry-looking mineral can contain a huge amount of water.
When the solar system first forms, the massive cloud of gas and dust traps the heat of the young sun. Where Earth forms, it's well over 1,000 degrees Fahrenheit. Too hot for such water-bearing rocks to form and build the planet. Yet soon after its creation, Earth manages to get water. Drake asks himself a new question. What if the early Earth traps water another way? A way nobody ever imagined.
One day I was drinking a nice cold drink, and I looked at the glass, and it had condensation on the outside of it, like this one does. You can see the water vapor on the inside if I run my finger around it. And I wondered if the same kind of process could have occurred in the disk around the sun 4.5 billion years ago. Could water have condensed out onto grains, much like it has onto this cold glass?
It's completely different to water-bearing rocks. If water vapor sticks to the grains of dust that build the planet, they could be the source of the oceans. An entirely new way for planets to form with water. He tests the theory with one of the main ingredients of planet Earth.
The green mineral in this rock is olivine, and olivine is the most abundant mineral that you find in the rocky planets. It's also the mineral that was abundant in the disk around the young sun 4.5 billion years ago.
He wonders if all the grains of olivine that form the planet have water stuck to them. He uses a computer to calculate the interaction between olivine grains and water vapor in the very early solar system. Water molecules stick to the olivine crystals.
So 30 grams of olivine allows me to absorb about 0.3 milliliters of water.
But can you capture enough water to fill the oceans? Drake has to scale up his calculations. How much water could stick to an Earth-sized pile of olivine grains?
Frankly, when we started these calculations, we didn't have a clue about how much water we could absorb. And we were actually astonished when we discovered we could get 10 times the amount of water that's currently in the Earth's oceans.
Professor Drake believes as the early Earth forms, it already has billions and billions of gallons of water. Water that sticks to the trillions of grains of dust that build the planet.
It's really exciting to have come up with a new solution to one of the most fascinating and important questions that humans face, and that is, why do we have any water? Because without water, we cannot exist.
But Drake's theory is new, and not everybody's buying it. It has a flaw even he can't explain. The type of water. Our water has a signature. The ratio of heavy to light hydrogen in the Earth's water tells you where it comes from. The source of Earth's water should have a matching signature. But the water that condenses directly from the disk of gas and dust around our young sun is very different. It would look and taste the same as Earth's water, but it would have 6 times less heavy hydrogen.
Now, I don't mean to pretend that we've got the entire answer yet, and until we can show we can get the right ratio of heavy to light hydrogen, we cannot be certain that this process is responsible for the Earth's oceans.
If Earth's water doesn't come from the building blocks that form the planet, and it doesn't come from comets, where does it come from? Professor Alessandro Morbidelli has developed his own theory.
All of a sudden, everything fits together. And you feel you understand a piece of your past that nobody was there to observe.
Are the origins of Earth's water finally about to be revealed? The origin of Earth's water is one of the biggest mysteries in science today. Scientists are looking for a match. There must be somewhere in space that has the same kind of water as Earth. The answer may be locked inside this lump of rock and metal. Few people know more about these meteorites than Gary Huss.
Well, I grew up in the basement of a meteorite museum my grandfather had in Arizona. And so I'd go up and look around at the meteorites, and by the time I was 2, I knew all of their names. Once you get bit by a bug like that, you can't get rid of it.
While comets are made of ice and dust and come from the cold fringes of the solar system, a meteorite comes from somewhere else. Orbiting the Sun between Mars and Jupiter are millions of lumps of rock and metal called asteroids. Some 200 miles across, weighing millions of tons. Leftovers from the formation of the planets. Sometimes asteroids collide, and fragments fall to Earth as meteorites. But what can they tell us about the origin of Earth's water?
The initial idea 100 years ago was that you had a major planet and it broke up and everything was dry and hot.
Looking at meteorites under a microscope reveals a different picture.
As we learn more about meteorites, it turns out that some of them are actually quite wet, a few percent water.
This is a slice of a meteorite, known as a carbonaceous chondrite. The bulk of it, the black stuff, is a mineral with water locked inside. This fragment of rock was once part of an asteroid that formed 200 million miles away. It reveals that at this distance from the Sun, asteroids formed with water locked inside.
There's water in the asteroid belt, and it's apparently always been there. We just didn't know how to recognize it.
Is there any water in the asteroid belt identical to water on Earth? To find out, Professor Huss measures the ratio of heavy to light hydrogen in the water-bearing meteorites. He can do this with an ion microprobe.
We were actually quite fortunate to get one of the very first of this newest generation of ion microprobe.
The machine fires a beam of charged particles at the meteorite. This expels all the hydrogen atoms in the water. The heavy hydrogen and normal hydrogen are then separated so he can measure the ratio between them. What Dr. Huss finds looks like a crucial piece of the puzzle. The ratio of heavy to light hydrogen in the water in asteroids varies. But some have exactly the same ratio as the water on Earth. It looks like scientists have finally found where Earth's water comes from.
So then the question is, how do the two things from different parts of the solar system end up with the same kind of water?
Chemistry can't solve the conundrum. But mathematician Alessandro Morbidelli has a radical theory that could explain how water from the asteroid belt ended up on Earth.
The idea was driven really by measurements, by the fact that the water on Earth is so similar to the water that we get from meteorites that come from the asteroid belt.
Morbidelli took a revolutionary look at an old subject, how the planets in our solar system were built. Before, scientists looked at the formation of the 4 planets closest to the Sun. They studied how matter near the Sun condensed into bigger bodies, eventually forming the planets Mercury, Mars, Venus, and Earth. Morbidelli has done something radically different. He's the first scientist to look at the formation of all 8 planets in the solar system as a whole. From Mercury, closest to the Sun, to Neptune, 80 times farther out.
The solar system is entirely interconnected, and we cannot study the formation of a portion of the solar system neglecting the other regions of the same system.
You can't study the planets in isolation because they're all linked by one force.
The only force that matters is actually gravity. So these things are relatively simple. We don't need to invoke strange physics or strange forces or dark matter.
As the planets grow, they interact because of gravity. Morbidelli recreates this interaction with a computer model, giving him a ringside seat at the birth of the solar system. About 1 million years after the birth of the Sun, the disk of gas and dust in the inner solar system condenses to form about 50 mini-planets. During the next stage, these mini-planets collide and form bigger planets. This demonstration shows what happens. The oranges represent mini-planets near the Sun. It's too hot for them to form with water trapped inside. As you move out, it gets colder. 230 million miles from the Sun, it's cool enough for mini-planets to form with water-bearing rocks. Green vegetables represent mini-planets with water.
The Earth eventually will have to form in this region, so in a region which is very hot, where nominally there should be no water.
If you look at the mini-planets close to the Sun, Earth forms from local material.
The mini-planets orbit around the Sun on trajectories which are almost parallel, like this.
Mini-planets collide to form the Earth. It forms from dry material.
But in this case, the Earth, because it formed from mini-planets which were dry, will also be very dry. Luckily for us, this is not what happened, so we need to revise our model.
Because Morbidelli looks at the solar system as a whole, the whole scenario changes. Enter a new player, Jupiter. Jupiter is the biggest planet in the solar system and one of the first to reach full size. It's 300 times more massive than Earth. And in the early days of the solar system, it's starting to throw its weight around. Represented by this silver ball, Jupiter's massive gravity disrupts the orbits of the mini-planets.
Now, the mini-planets, in particular those farther out, have a more irregular motion, and in this way, the mini-planets can mix with each other.
Earth now forms wet. Look at the formation of all 8 planets at once, and Earth forms from a mix of mini-planets, some dry, some wet. This model explains how Earth came to have similar water to that found in the asteroid belt.
All of a sudden, everything fits together. And you feel you understand a piece of your past that nobody was there to observe. These moments are fantastic. There are just a few moments like that in a career of a scientist. But even if it happens once every few years, those moments are so exciting that they are worth years of work.
Morbidelli's idea is now the leading theory of how Earth got its water. But it's not the whole story.
For the moment, it is the best answer that we have. But as we say, the devil is in the details. There are certainly some details we don't understand, so we need to keep working until we understand all of them.
The question is, what happens to the water on Earth during the continuing collisions with mini-planets the size of the Moon and Mars?
The energy of this collision is so high that it's capable of melting the entire Earth. In addition, it actually vaporizes some fraction of the Earth's rock.
If these collisions vaporize rock, how can the water survive? The origin of Earth's water remains unclear. Scientists have theories that can get the water to Earth, but can they keep it here? The final stage of Earth's formation is a series of cataclysmic collisions. Can water survive the process? The answer is in the night sky. Robin Canup has been working on the formation of the moon for 13 years.
I think people are particularly fascinated by our moon because it's been our companion throughout all of human history and throughout all of the Earth's history. Every human that has lived has gazed upon the same moon.
The moon was formed by a collision between the early Earth and a mini-planet.
The leading idea for how the moon formed is known as the giant impact theory. Just as the Earth was finishing its formation, the Earth experienced a collision with another planet-sized object, something that was smaller than the Earth, but still comparable to the current planet Mars in its size. So this was an enormous collision.
The last of several giant collisions between mini-planets that formed the Earth. Why does this collision result in a dry moon and not a bigger Earth? Robin has developed a computer model to find out. The key turns out to be the angle of impact.
When this collision first comes in, it's at an oblique angle. The impacting planet is sheared apart into this long arm of debris that then wraps around the Earth to form a disk.
In no more than the span of a human lifetime, the disk of debris condenses and forms the moon. So why isn't the moon wet?
If you distribute that rock out into a disk around the Earth so that the disk is very spread out and there's a lot of surface area over which that rock can lose its water, then the water will tend to evaporate and be lost.
The model explains why the moon is dry, but it doesn't explain what happens to the water on Earth.
The moon-forming impact is an event of such a scale that it's almost difficult to comprehend. If you've ever visited a volcano and seen the molten lava coming out of the Earth, that's what we mean by molten rock. That would have been the coolest material on the Earth after this impact. If you continue to heat that material even more, it will eventually actually vaporize. The moon-forming impact was energetic enough to do both.
These cataclysmic impacts should have driven off any water on Earth. The impact occurred about 4.5 billion years ago. And as this is the last cataclysmic collision that planet Earth suffers, the date is vital. Professor Moiges' zircons reveals Earth has water 4.4 billion years ago, very soon after the collision that formed the moon. If the collision had blasted Earth's water into space, where did the water in the zircons come from?
Since water was present here in liquid form and abundantly very early on and soon after the moon forming event, it means that either the water was delivered very rapidly right after the moon formed, which I think is highly unlikely, or water was already present on or within the Earth before the giant impact that resulted in the formation of the moon.
So the Earth's water survives this last cataclysmic process of planet formation. But how? Professor Drake thinks the water has been here from the start. He has a theory about how it survives.
So the collision of a Mars-sized object with the Earth is an incredibly violent event. It'll melt the Earth. Now the obvious question is, if the Earth went through such a violent event, how did it manage to keep its water? Most people think that if you heat something up, you boil all the water off, but that's not actually true. Any water that was in the Earth will be dissolved into that molten rock. That molten rock or magma is literally a sponge for water. You can dissolve vast amounts of water in liquid rock.
The early Earth is a giant fireball of molten rock. Dissolved inside are billions of gallons of water. But how does this rock become our blue planet?
This red-hot molten Earth is going to have lots of water in it. And that water's got to go somewhere when the planet cools down.
The rocks in this Arizona desert reveal what happens as the cooling rocks solidify.
Rock that crystallizes deep inside the planet will have the water kept in the minerals that crystallize. Here we have some micas. This happens to be a granite. And that water will be kept in the planet for 4.5 billion years.
Rocks that solidify deep in molten lava can hold water. But lava near the surface forms a different type of rock.
Any rock close to the surface, this one, for example, right here, you can see the holes in it, is going to lose its water. It's going to make little bubbles, which is what these holes are. Now imagine that there was rock like this all over the planet crystallizing. Water gets out into the atmosphere. Just look at the mountain range behind me and imagine the amount of hot, steamy water that could be coming out of these rocks as they crystallized.
All over the planet, water vapor escapes from the cooling rock. Earth's atmosphere is dense with steam. 100 million years after the impact that formed the moon, Earth has cooled enough to form a crust.
And you'll have boiling hot rain coming down onto the surface of the planet, running down in rivers, and eventually making the oceans.
But the story is still missing a chapter. Many scientists believe Earth has more than one source of water. Where did all of Earth's water come from? According to the leading theory, water arrived when mini-planets from farther out in the solar system collided with the early Earth. But scientists suspect this isn't the whole story.
I personally think there's more than one way to get the water to the Earth.
Like comets. Analysis of comets shows they couldn't be the source of all our water.
We can be pretty sure that comets must have brought in some of the water, because we know comets must have hit the Earth. But the question is, how much? What is the fraction that they contributed?
The solar system may have furnished another source of water.
We've been hit by comets and asteroids, and some of the water may have come from there. But for me, it's a no-brainer. At least some, if not most, of Earth's water had to come from absorption of water under grains before the planet ever formed.
But did these different sources bring enough water to Earth to support life? It's now impossible to work out how much of Earth's water comes from which source, because the water has been mixing for over 4 billion years. And over all that time, Earth's water has not only mixed, but changed.
The Earth's oceans basically have gone through a lot of processes since the Earth formed. There's rain and snow, and all of these things have caused the composition of the water to change a little bit.
By how much the water has changed, nobody knows. But there's a place where we might find out. A volcanic island chain in the middle of the Pacific. On the Big Island, Hawaii, Dr. Gary Huss is searching for the oldest water on Earth.
The Hawaiian Islands volcano is basically what's known as a hot spot.
A place where lava steadily oozes from the Earth.
The rocks that we're standing on in the Hawaiian Islands come from the very deepest part of the mantle of the Earth, thousands of miles below the surface. And it provides us a sample of material we could never get any other way.
When he looks at water locked in rocks drilled on Hawaii, Huss is actually looking at water from the middle of the Earth. Water unchanged since day one.
If you want to look at what the composition of the water on Earth is at the time that the Earth formed, this is the only place you can look.
Can Huss find evidence that there's primordial water deep inside the planet?
Oh, it's one of these guys? Oh, that's neat.
His approach is unprecedented, and early results suggest he might be onto something.
Well, this is good. This is a great sample for your purpose.
When we first found the hints, we definitely got excited about it. It does look like the water from deep in the Earth is different from the oceans, and it's different significantly.
So different, it could be primordial water, untouched since the birth of the planet. This research could ultimately deliver extraordinary answers to the question of the origin of Earth's water. And Hawaii isn't the only test site. The team is also sampling water from another hotspot, Iceland.
If we can nail this down for, say, the Hawaiian volcano, and then we can go to the Iceland hotspot and we get a different answer. Not only now do we have differences between the deep water and the surface water, we've got differences between a volcano on this side of the Earth and a volcano on that side of the Earth. There may be evidence for more than one source at this point.
One day, deep inside the planet, they may find reservoirs of primordial water different from each other. Such a discovery would mean one thing: our water must have different origins. The implications are profound. For years, astronomers have been working toward one goal: scouring the skies in search of another planet like Earth. A rocky planet, just the right size and just the right temperature for liquid water and life.
We know now of 250 other systems that have planets in them, and we haven't found an Earth yet.
Billions of systems are yet to be explored, so the numbers are on your side if you're looking for another Earth.
We have 100 billion stars in our galaxy. Of them, we think about 10%, so 1 in 10 is a sun-like star. And we think that maybe 1 in 10 of those stars has planets. So that's about 1 billion stars in our own galaxy we think would have an Earth-like planet in it. Now, whether it has water on it is a different story.
Do any Earth-like planets out there have water? Could any support life? Today's telescopes can't answer that question, but computer models can. Dr. Sean Raymond has devised one.
We take our cues from observers. So with telescopes, people go out and find giant planets orbiting other stars. Then we take the orbits of those giant planets and try to figure out, in that system, could you still form a planet like Earth?
Raymond's computer model shows as planetary systems form around stars, some Earth-like planets end up with water.
We're modeling the formation of a planetary system here. All this red stuff is dry, the blue stuff is wet.
He starts with lots of mini-planets. Far from their sun, the blue ones have water. Closer in, where it's hotter, the red ones form dry. As the planets form, they start to cool. Like Earth, any planet warm enough to have water must orbit in the dry zone.
This guy right here is going to end up being a pretty good Earth analog.
The model shows how wet mini-planets from further out are pulled in to collide with a mini-planet in the dry zone, like Earth.
And there you just saw it turn from red to yellow to green. That's water delivery happening right there. And by the end of this particular simulation, it's very wet.
The result is a planet in just the right place for water, another Earth. Using the model, Raymond can calculate what's needed to form other Earths and how many there might be.
Then we say, what if things were a little bit different, like we think they are around this other star? How would that affect the formation of planets like Earth, and how would it affect water delivery to those planets?
If Earth's water was delivered in more than one way, via comets, and with water as one of its initial ingredients, suddenly, the chances of finding an Earth-like planet with liquid water have just shot up. So too have the chances of finding alien life.
This is a big deal because are we alone in the universe, right? No one knows for sure. Everyone's excited about life on other planets. And what we're doing is one step towards trying to find life on those planets. It's really cool. I mean, it's very exciting.
And because scientists now think planets can get water more than one way, they're more confident than ever about the answer.
When people ask me if there's life out there, I say yes. And is there life like we know it, with a rocky planet where water has been brought to it? I think the answer again would be yes.
So by finding out how Earth got its water, we can find out how likely it is that out there somewhere, maybe millions of light years away, there are other alien forms of life.